For coming. I really appreciate you being here to hear about OpenStack. It's been a big topic this week. It's something I'm very passionate about, so I'm happy to be here to talk to you guys about it. So what I want to talk about specifically is OpenStack architecture. But before I do that, I want to introduce myself. So my name is Russell Bryant, and I've been working on OpenStack for Red Hat for about a year and a half. And my particular role in the project right now is I'm the project technical lead of the OpenStack Compute project, or codename Nova. And there's a couple of contact bits there for me. I'm on Twitter as Russell Bryant, and you can email me as well. And so I've only been doing this for about a year and a half. So before this, I worked on an open source telephony project called Asterisk for about 7 years. So what are we going to cover today? So there's been a lot of talk about what OpenStack is. I'm going to spend just a few minutes on it, making a few points that I want to make as they relate to the architecture of the project, because I think they're important. And then we're going to go through all the projects. I want to talk about concepts that are important to the project. I want to talk about how it works, what services make up that project, and also what it looks like when you take that service and start scaling it out. And also want to make a note now, there are session evaluation forms that you should have received when you came in. Please fill that out. I would really appreciate it. And if you don't have a pin, I put a box of pins out there for you, so you don't even have that excuse. So I'd really appreciate that. That'll help me, and it'll help the conference in the future as well. OK, so onward. What is OpenStack? Make a few points here. So it's compute, it's networking, and it's storage. It's made available to you as building blocks for your applications. It's the cloud, right? So it's public or private cloud. But what does it mean to be cloud? What are some of the things that make this platform different from another virtualization platform? So I'm going to make a few points because they kind of impact how we build this thing. So the first is that it's self-service. And what that means is that when you need infrastructure, you get it, and you get it yourself, and you get it now. And so you don't have to go through another person. You don't have to go through another team. You don't have to file tickets to get a server. You get it now. And the way you do that is you're given APIs that you can access directly to create your infrastructure, or there's a web dashboard available as well. So you go to the web UI and create what you need. Another thing, pay as you go. So in a cloud environment, you're not having to reserve something in advance. You're not reserving for a month or a year or some period of time. You get it now, and you only pay for it for as long as you use it. So if you create a server and use it for an hour, that's all you pay for. And that's really, really nice for if you're in an environment that needs to dynamically scale up and scale down depending on whatever it is. Let's say your company gets featured on CNN.com one weekend, and so all of a sudden you need to triple your capacity for your website to handle that load. You can do that for as long as you need it, and then scale it back down. You only paid for what you use. So that's an important thing to me of what makes something cloudy. Another thing is that you're given the illusion of infinite capacity. And what I mean by that is you have access to this pool of resources. You don't know and you don't care about how that's built physically. You don't need to know. You just need to know that you can go there and ask for what you need when you need it. And the other thing is massive scale. And that's something that we spend lots of time on in the OpenStack project. We want this to scale from anywhere from one node all the way up to many, many thousands of nodes. I already know of deployments. One, for example, that has a compute deployment of 16,000 nodes. CERN is another one who said that they are planning to scale up to maybe 15,000 compute nodes in the next couple of years. There's multiple public clouds built on this stuff that are very large. So we've already sort of achieved this to some degree, and we're doing a lot of stuff to make this even better, to go to many tens of thousands of nodes if necessary. OK, so those are some points about what makes OpenStack. But how does it work? So let's go through the architecture. So here's the first view of the architecture. It's we talked about before that it's compute, networking, and storage. The first level is that the way we accomplish that is through a number of projects. It's not one monolithic thing. It's split up into multiple projects. And so we're going to go through each one of these. So each one of these has a team of people that's working on it to solve a subset of the problems in OpenStack. And Red Hat, by the way, has people contributing to all of these things, which I'm very proud of. And a few things I want to mention here as well that are relevant. So there's another thing that's considered a part of OpenStack called Oslo, but I'm not going to talk about it because Oslo is a common library. So it's basically a library of shared code amongst all these things. But there's a team of people that work on that, and that's important. Now, when OpenStack started, just not long ago, it started as 2 projects, and now I'm showing here that there's 9 of them. So we're continuously adding them, and there's a process called incubation. So a project gets started, it goes through incubation, and then it's officially an integrated part of the OpenStack project. And so these 9 are integrated right now. We have 2 projects under incubation. One of them is called Trove, and that is a relational database as a service project. And there's another one called Ironic, which is a bare metal provisioning project. So those two are under incubation, and I would expect them to be fully part of OpenStack at some point in the future. So let's start diving in. Okay, so the first one is the identity project. Now, its official name is OpenStack Identity, but it has a code name called Keystone. So every project has an official name and a code name. The code name is really what you're going to hear most often. It's typically shorter. It's what we actually use in the code. If there's commands associated with that project, it's the code name. So a Keystone command, for example. That's what you're hearing in conversation. So I'm going to introduce each project in terms of its official name and its code name. So Keystone. Now, a bit about Keystone's name. I think it's rather appropriate and kind of interesting. So in architecture, if you have this stone arch, the keystone is the stone at the very top. It's the one you put in last. It kind of locks it all into place. And that's appropriate for Keystone and OpenStack because it provides this concept of identity to have users in your cloud. And without an account, you can't do anything useful. So I think that's a pretty good name. So some important concepts about Keystone. So the first one is tenants. So tenants are a group of users. Now, a group of users share resources, so they all have access to the same servers or the same networks or the same block storage or whatever that thing is within OpenStack. They share that. And that could be a team within your company. It could be an entire company if you want. I mean, you kind of use it how you wish, but it's the way you group users together that can share resources. So Keystone defines users. It defines roles for those users. The only thing we use in reality with the roles thing is administrator, whether you're an administrator or not. And tokens. So tokens is really important. So the way Keystone works, it's a standalone service, and you talk to it, and you authenticate, and it returns a token to you. And that token is what allows you to go talk to all the other OpenStack components and use those APIs to get anything done. And the final thing that is also very important about Keystone is it manages services. And what I mean by that is it's a service registry, and it's used as a way to discover services as well. So when you go to talk to an OpenStack cloud, the only thing you need to know is the API endpoint for Keystone. So you talk to that, and you can and it returns to you a list of all the other services that are available in that cloud. So how you talk to the compute API and all the other APIs we're going to talk about here throughout the rest of the presentation. So that's the other important bit of Keystone. Okay. Now, so what does Keystone look like architecturally? So Keystone is a single service. There's just one service that runs, and it presents a REST API to you as a user. And it has three sort of conceptual components internally. The first one is a token backend, and so when you authenticate to Keystone, and it gives you a token, it's keeping track of all the tokens it's handed out, and so that's that part. There's an identity backend, which is all the users and their passwords, and then services. So I talked a minute ago about how Keystone is also a service registry to allow you to discover all the other services in your cloud. There's a backend for that. So all of these things are pluggable. So there's different ways that all the information can be stored. All of them support Relational Database, so you could just be using MySQL to back all of it. The identity part, you can use LDAP instead. So if you're already using LDAP to manage users in your environment anyway, you can hook up Keystone to it. And then the services thing, you can actually just back it with a flat file instead of putting it in a database, and then it gets cached in memory instead of having to hit a database every time you request it, because that thing the services stuff usually doesn't change very often. Okay, so that's the parts that make up Keystone. So if you're going to take Keystone and use it in a much larger environment, how do you scale it out? So this is what that looks like. Now this pattern is something you're going to see a bunch throughout all the OpenStack components. So what we have here is the blocks here in the middle that say Keystone. That's the same thing that we were just looking at in the last slide, but we're going to run as many of them as we need, and this is called horizontal scaling. So instead of just trying to make one node bigger and faster, you run it on as many nodes as you want, and you put a load balancer in front of it. And so the load balancer, with Red Hat ships a software-based load balancer called HA Proxy, so that could be HA Proxy there, or you can use a hardware-based one as well. There's a bunch of them out there. And then all the Keystone services are just going to use that same storage backend, and so you have to scale your storage backend as well as necessary. But that's what scaling looks like, and this horizontal scaling thing is really important, and we're going to see it a bunch throughout all the services. Okay, so that was Keystone. So it's back to the list of projects here. The next one we're going to talk about is the dashboard, and its code name is Horizon. So this is a web UI, right? And so the web UI gives you this nice view of all the different things in OpenStack, like the horizon of OpenStack. It's a pretty good name. So it's a self-service UI. So you go in here, you log yourself in with your account from Keystone, and then you can go create all the resources that you want. So here's another example. You've got, if you want to create yourself a virtual machine, it gives you this nice sort of wizard to go through and give it a name, select what disk image your VM is going to be based off of, and also choose which resource, like what kind of resources it's going to get, how many CPUs, how much memory, how much disk. So all that stuff is presented to you from the Horizon UI. Once there's also a place to manage all of the things that you've already created. So all the VMs that you have running, you can perform all kinds of operations. You can change networking parameters. You can add additional IP addresses to them. You can pull up a VNC console to log into it if you want to, and you can manage the VM's lifecycle. So you can reboot it, terminate it, and so forth. Okay, so that's view of what Horizon provides. Now, how's it built? Let's get back to the architecture part. So it is a Python WSGI application. And by the way, almost all of OpenStack is written in Python, if you care. So it's written in Python, and it's using Django. And it's mostly stateless. And all it is, it's a nice interface to all of the APIs. So everything that you see in this web UI is something that's possible through the UI, through all the APIs. So you can scale this out, and in fact, the way you do it is horizontally. So you run as many of them as you need, like the last one. So what's different about scaling out Horizon from the rest is that all of these different instances of Horizon have to share session state. And this is actually handled by Django. We didn't, it's not something that we did in Horizon to make this work. Django has a concept of session engines, and you have to pick one that works across multiple instances. So there's the default is just local cache, so local memory. But there's you can use memcache, you can use a database, you can use a combination of a database and memcache, and there's one backend that's entirely cookie-based. So, once you scale this out, go check out the Django documentation, read up on the different session state backends, choose one that makes sense for you, and that's how you scale it out. And so all of them are using the same OpenStack APIs. So no matter which one you happen to hit, you're going to get the same information. Cool. So that was Horizon. Now let's go back to the list of projects. The next one we're going to talk about is the OpenStack orchestration project, and its code name is Heat. So when this project was started, when they were coming up with the name, they said Heat keeps the clouds up, which was a clever name because, as you'll see in a minute, Heat does keep your cloud deployment up. So why is Heat awesome? I think Heat is really awesome. And if you were at the keynote this morning, you saw a good demonstration of it. So what Heat does is it provides you the ability to define your application in terms of a template. And so if usually your deployment into a cloud is not as simple as just one virtual machine. Usually it's a lot more than that. You've got maybe 3 virtual machines and a database and maybe some special networking configuration. And then even within each virtual machine, like what packages do you need to install and some other bootstrapping information. So it allows you to define this in a template and then give that to Heat. And then Heat turns around and talks to all the other OpenStack APIs to deploy that. And so what that gives you is the ability to, you can version your deployment just like you would version software. It's like, version it like a text file. And it's, so you can have a complex deployment and it's very repeatable. So this morning in the keynote, they demoed deploying OpenShift using this method. So they have a template for deploying OpenShift, and it also provides, you can do some monitoring of what you have and do auto scaling. So this morning, when you saw that, like as in OpenShift, they were launching new applications, it got to the point where it needed more capacity. So he saw that it needed more capacity and automatically created a new VM to expand it. So that's what Heat can do. And I can also scale back down if necessary. So how does Heat work? Let's take a look. So it presents an API as a Heat API service. There's a REST API, and it also supports Amazon's CloudFormations API. All right, so this is the first time we see AMQP here, so I want to talk about that for a second. So AMQP stands for the Advanced Message Queuing Protocol, and it provides scalable messaging between applications. So there's a number of OpenStack components that use this internally for multiple services to talk to each other. So Heat is the first one we see that's doing that. So you've got the API that's presenting the public API. Then internally, you have the API talking to Heat Engine. Now, Heat Engine is what's doing the real work as far as taking that template and then talking to all the OpenStack APIs to get the work done. So now let's talk about how this scales out when you need to use this in a really large deployment. So the top part there, the API and the load balancer, is just like the rest of them. You run as many as you need. The load balancer takes care of that. And then the next part, heat engine, you can run as many of those. This is horizontally scalable as well, but the way the load's balanced is different. So it's using the messaging infrastructure. So what we do is it queues up all the requests in the messaging infrastructure, and then you have all of your heat engines picking them off the queue and processing them. So, and the other nice thing that Heat did is that instead of having a database shared amongst all of them, there's a database local to each one, so you don't have to worry about really complicated database scaling for this. So it's local to each one, so that's really nice. And then they all talk to the same OpenStack APIs. So that's how you scale out Heat. OK, so next service here. Service number 4 is OpenStack metering, and its code name is Ceilometer. So what is metering all about? So a meter is any type of usage data. So billing or chargeback is an important part of a cloud deployment, and this is sort of the fundamental layer to that. So before you can bill anyone, you have to know how much they use stuff. And so that's what this is all about, is tracking how much stuff was used, and then you would build your billing stuff on top of this. So that could be something like CPU hours, how much bandwidth you consumed, things like that. So the way it collects all this, so its purpose in life is to collect all this data from all the rest of the services. Now, most of the data comes in terms of notifications. And the notifications use AMQP, kind of like which I just introduced when we're talking about Heat. So it uses this messaging infrastructure. All the services, as you're consuming resources, they're firing off notifications, and Ceilometer is consuming them, keeping track of it. Now, there's also some polling if necessary. Like if there's some information that Ceilometer wants to track, but it's not in a notification yet, there's a couple of places that can do polling. One of them is what's called the compute pollster. So there's a service that runs on every single compute node that's running a hypervisor node that can poll for information that it needs. And the other one is just a central pollster. So if you wanted to write a plugin that polls some API for whatever it is you want, they provide a place that you can plug in to do that. And then you have the collectors. So the collectors are these services that collect all the data from all these different things. OK, so those are sort of some concepts. Let's get into what does this look like. So here's a really nice conceptual architecture diagram. And what we have here, so these sort of boxes here to the left are all the different OpenStack services. And then they're all, so these sort of blue part at the bottom, they're firing off these notifications onto a message bus. And then you've got the pollsters at the top right, which are also firing messages off into a message bus. And then you have the collector at the bottom right, which is collecting all of the messages from all these sources and putting them into a data store. So that's effectively the flow of all this information in Ceilometer. Here's another view of how Ceilometer works. The one difference with this diagram is it shows it has an API. So you have this data store here sort of in the middle. And there's also an API service that your billing system would be talking to get access to all this usage data. And so how do you scale out Ceilometer? So the API gets scaled out just like everything else. You horizontally scale it, put a load balancer in front of it. You can run as many of them as you need to. The compute pollsters, or the compute agent, runs on every single compute node, so that's not an issue. The collector that's sort of consuming all of this, you can run as many of those as you need to, and they'll sort of take turns consuming the data off the message bus and shoving it into the data store. So basically, all of this is horizontally scalable. The only catch is the central agent, the central pollster. It's sort of left up to, so that one, it doesn't actually do anything by default. It's sort of it's a place that you can plug in your own logic if needed, and it's sort of left up to you to scale that out if you need to. But the good news is it's not used by default, and you probably don't need it. So that is Ceilometer. Let's jump to the next service here. So back to our list. The next one is OpenStack Object Storage, and its code name is Swift. Swift is one of the founding projects of OpenStack, one of the first two. And it allows you to store and retrieve blobs of data. So the concepts in Swift are actually fairly simple. You have an account, and you have objects, which is just your blob of data that you need to store. And you have containers, which allows you to organize the data that you're storing. And then it has an internal data structure called the ring. Now, as a user of Swift, you don't know about it, but as an administrator deploying it, you do know about it because you have to tell Swift information about your deployment, like how many nodes you have and so forth, to allow it to build this data structure, which is effectively a distributed hash table. So let's look at what this looks like conceptually. So there's sort of two different node types if you're deploying Swift. There's an API node, and there's a storage node. So at the API node, you have a proxy service, and then you have that you see sort of the internal data structure of the ring there, and that allows it to, that's what it uses to figure out what storage node to talk to get the data that you're looking for. And then the storage node, which is storing a subset of your data, the objects, the containers, the accounts. And the storage nodes hold replicas of the data, so it automatically replicates the data across multiple nodes as you configure to do so. So yeah, that's the 2 node types. Now let's look at how you scale this out. So it looks really similar. Yet again, the API part, the proxy, is horizontally scaled out. So you run as many as you need to with a load balancer in front. And then you have the storage nodes that you can run as many as you need. Now you can add and remove storage nodes as much as you want. And you just tell Swift that you've done that, and it automatically rebalances. It'll sort of regenerate its ring, and it'll rebalance the data and make new replicas of data if it needs to, good stuff like that. So that's how a scaled out Swift deployment looks.
Real quick, is the performance of Swift impacted when this is happening?
The question was, is the performance of Swift impacted when replication is happening? Is there a way to stop it? Well, presumably you'd want to stop it. You wouldn't want to stop it. I mean, you want to make sure that all your data is there. I can't really speak to the performance of that. And by the way, I guess I should have mentioned this earlier. I should have some time at the end for questions. So if you have any more, let's just hold them to there. Okay, so the next service is an OpenStack image service called Glance. And so Glance is just a registry for disk images. So the disk images for creating virtual machines. So it stores those, and it also stores metadata about the VMs. So some of the metadata is stuff like what's the name of it, how big is it, access control, is this something public that everyone using the cloud can use, or is this something private, just for you to use? But there's also some really interesting metadata that you can do. So some images may have different capabilities as far as virtualization goes. Like in the compute project, we'll use VirtIO for networking by default, for example. But if you have like an old Windows guest or something that doesn't support it, you can put some metadata on here to say, instead of using that, use an emulated network device instead, and it'll do so. So there's some good metadata that you can set. And the other thing about Glance is there's different storage backends. So one of them is Swift. So if you have a Swift deployment, you can just have have Glance talk to Swift to store the images, but it also can just be file system backed. So if on a really small deployment, just a local file system, or what we've been recommending to a lot of people is to use GlusterFS or Red Hat storage to back sort of a scaled out Glance deployment. That works really well. So what does Glance look like from a services perspective? It presents a REST API from a Glance API service. There's also a Glance registry service that also has a REST API, but it's an internal REST API. You don't have to worry about it. Glance API uses it. So Glance registry is responsible for the metadata, and it stores that in the database. And then you also have the image storage, whichever one you chose. So that's kind of the pieces that make up Glance. Now, if you were to scale Glance out, it's just like the rest. You horizontally scale it. Run as many of them as you need to, and put a load balancer in front. And they all point to the same storage in the back end. So next service, block storage, and its code name is Cinder. The block storage service, it provides the concept of volumes and snapshots. So these are block storage volumes that can be attached and detached from running virtual machines. Now, the actual attaching part is actually handled by the compute service. So really all that happens in Cinder is creating it and destroying it and doing the snapshots. And there's different backends to it. So this is actually a really hot area where different vendors are providing plugins. I was actually just talking to someone right before the talk where his company is working on a backend for this. Now the default one is LVM based. So you have a bunch of volume nodes and it's just using local storage. So you give it a volume group, and every time that you request a volume, it creates a new logical volume and exposes that to the virtual machine over iSCSI. Now there's a bunch of vendor backends to talk to various storage appliances. And those typically also use iSCSI as their interface to virtual machines. And there's a couple others that work different. Those are NFS and GlusterFS, or Red Hat Storage. Those are file-based. So the volume nodes just have access to the shared file system. When you create a volume, all it does is create a file there, and then the compute nodes, or the hypervisor nodes, have access to that same shared file system, and it uses those files as the backing for the volume. Okay, what does Cinder look like from the services perspective? It has a REST API. It's exposed by the Cinder API service. Now there's a couple of other services here that do interesting things. So there's a thing called Cinder Scheduler, which you'll see again later in another service. But Cinder Scheduler is responsible for doing the logic for placement. So when a request comes in and says, I want a new volume, the scheduler decides where that actually goes, on what volume node. And then you have Cinder Volume, which is managing storage on each volume node. Now, so if you're going to scale this out, the API scales horizontally with a load balancer. And as with talked about in Heat, there's horizontal scaling provided by the messaging infrastructure as well for both Cinder Scheduler and Cinder Volume. OK, so the next service is OpenStack Networking. Now, I'll put ... there instead of its code name. The code name was Quantum, and I still call it Quantum most of the time. Quantum is a problematic name, has a trademark conflict. So it's in the process of getting renamed, and they haven't come up with a new name yet. So we're supposed to call it OpenStack Networking, but that's kind of long. So I'll probably just keep calling it Quantum for now. So Quantum. What are some concepts? So this project provides you these sort of dynamic networking for your cloud deployment. And so you have networks. So a network is an isolated layer 2 domain. And so you create these networks, and it's what allows your virtual machines that you put on that network to talk to each other. You create routers. So routers provide connectivity to external networks, but it also allows you to connect multiple of these layer 2 networks together. You can create subnets. So subnets are a block of addresses that you allow your VMs to use. And then you have ports, which are the sort of virtual ports on a network that virtual machines plug into, and allows you to sort of hot plug virtual machines to all these different virtual networks that you've defined. So just like Cinder, Quantum has a whole lot of plugins for different vendors' networking technologies. There's some open source ones included. There's one based on Linux bridges, but I guess the more hot one is Open vSwitch based. So let's look at what the architecture is of the OpenStack networking project. So up top here, you have an API node. And the API node runs, services the API. And then it also has a plugin. So the plugin is specific to whatever networking technology you've chosen. Now, and then it uses messaging. So it uses a message broker, AMQP, like a number of others, to talk to other nodes. So there's compute nodes and there's network nodes. So on each compute node, these are hypervisor nodes. There may or may not be a layer 2 agent there. So if you're using the Open vSwitch plugin, there will be an agent running on the compute nodes that does local network configuration there as needed. And there's a few other agents that run as well on network nodes, and that is the DHCP agent. So DHCP agents provide DHCP on a network, as you might imagine. And there's an L3 agent. So the layer 3 agent is what provides the gateway to other networks as needed. It also provides floating IP support. So floating IPs are typically used as the like public IP addresses that you can move around to different virtual machines. There are security groups. So that's like firewall rules. That's handled by the L3 agent. As well. So now some new stuff happening in this space that's not reflected here because it's still being worked on is load balancer as a service and VPN as a service. So those things are also going to be exposed here. And so the way this scales out, the API scales out just like everything else. And then you can run the services that are talking via AMQP. You can run as many of those as you want to as well. So for each DHCP agent, it can be responsible for one or more networks. Same thing with the L3 agent. It can be responsible for one or more networks as well. But you can run multiple of them. So that is the networking project. All right, so the last project I want to talk about here is OpenStack Compute, which is Nova. And it's my favorite, but I'm a little biased. So what does it provide? It provides instances or servers. And it also provides flavors or instance types. That's the sort of predefined sets of resources that you can allocate to your virtual machine. How many CPUs, how much RAM, how much disk, and so forth. And it's also a plug-in layer for virtualization drivers. So that's for supporting all kinds of different hypervisors. KVM is the most popular by far. But it also supports a number of others. Interestingly, it also supports bare metal provisioning, so you can use the same infrastructure to provision bare metal. It has two APIs. There's an OpenStack API, it's a REST API, and also supports the EC2 API, at least some subset of it. So what does Nova look like from a services perspective? It looks almost identical to Cinder, and that is because Cinder was originally a part of Nova, and it kind of got moved out to its own project and then just works the exact same way. So it looks very similar to it, and the only difference is instead of a volume service, you have a compute service, which is running on every hypervisor node to manage local VMs. And you also have a conductor service. Now, the conductor service is a little bit kind of interesting, and so for security reasons, we want to isolate these compute nodes that are running VMs as much as we possibly can. And so because of that, the compute service does not have direct access to the database. And so there's another service that has to perform some tasks on behalf of a compute node, and that's where the conductor service comes in. So if we wanted to scale this out, it looks similar to how Cinder does. You horizontally scale all of it as needed. Now this works to a point. So people are using Nova for really, really big stuff, and it gets painful when you start to get to many thousands, or if you get up to over 10,000 nodes, it starts to get painful. And the pain points are 2 points. There's sort of 2 things here that sort of look like a central part, sort of a central thing instead of scaling out, and that's the database. That gets painful at a point, and then the messaging infrastructure also gets painful. So there's a messaging, a message broker service that runs, and at a point that it gets hard to scale that as much as needed for this. So that's why in the top right here, I said this is how you scale Nova step 1, so to a point. But we have another level of scaling in Nova. So now I want to show you what that looks like. So what that looks like is something we call cells. Now, each cell has its own database and its own message broker. And so you have compute cells that are mini hypervisor nodes, and then you have an API cell, which is the sort of single API entry point for all of the compute cells underneath it. Now, another cool side effect of this is that you can now have different compute cells geographically distributed. Before this, you couldn't have a single compute API, but your compute nodes in different geographic locations. But with a cells deployment, you can do that. So now, so this is sort of like the zoomed out view of what cells look like. And so now I'm going to tell you, or show you rather, what's inside of an API cell and what's inside of a compute cell. So the first one is a compute cell. So a compute cell looks almost like what Nova itself looked like earlier, but instead of the API at the top, we have a cells service. But other than that, it's got the other services, a whole bunch of compute nodes inside of it, its own message broker and database. But the cells service is what's responsible for like federating with all of the other cells that are out there, and it talks to them using AMQP. Now the API cell that you have at the top is as many API services as you need, load balanced, and then it has a cells service, and the cells service will talk to all of the compute cells as necessary. So zoom back out, and this is what you get. So you have these, you can have these cells, and they're federated, and that allows us to a whole another level of scaling, which to a point of, I don't know, we haven't really hit it yet. So this is working pretty well so far. Now, so time to take a deep breath. We've made it through all the services and talked about how they work and what they do. So let's take a step back out here and talk about what happens when you want to perform an operation. So I'm going to walk through and talk about when you boot an instance, what do all these services do? So let's boot an instance. Step 1, as a user, you're going to talk to the identity service or Keystone, and you have to get in a token. You're going to authenticate. Keystone returns a token to you. So now you've got a token in your hand. What do you do next? Now you go talk to the compute service, and you give it your token, and you say, I would like a server, please. And then it has to process that request for you. So zoom in on compute real quick. So when that request comes in, it comes into the API service. The API service is going to send a message over to the scheduler. The scheduler has to perform some logic based on the current state of your cloud to determine which hypervisor node that VM should live on. And once it makes that decision, it's going to send another message over the AMQP message bus to the correct compute node. And so once it lands there, the Nova compute service on that hypervisor node knows that it needs to create a virtual machine, but it has some additional information it needs to gather first. So from there, we go back, zoom back out, and it needs to go talk to Glance or the image service. So the compute nodes do cache images to a degree, so it doesn't always have to go download an image, but if it has to, it'll go over there and download it. Talks to the API, and the API will stream the image data back to the compute node. Once it has the image, The next thing it needs to talk to is Cinder, or the block storage service. If, as a part of your request for your virtual machine, you said, I want a virtual machine, but I also have this volume, and I want this volume attached to it when it boots up, then it goes over there and talks to the block storage service saying, I had a request for this volume. I need the connection details. So it'll give you back the iSCSI connection details needed. And the final thing it has to talk to is the networking service. So when you request your VM, you say, I want this VM on these networks, the networks that you've defined in the networking service. And it's going to go there and get the information from Quantum that it needs to make that work. And finally, we're back to the compute service. It has all the info it needs from all the others, and it can actually boot your VM. And you're left with a server in the cloud. Yay. Cool. So that's how it works. So some more information. There's a couple of things that I would recommend. Tomorrow morning, there's a lab deploying OpenStack on Red Hat Enterprise Linux infrastructure. It's from 9 to 11 a.m. Should be on your schedule. I'd recommend that. And if you haven't tried RDO, I would definitely recommend checking that out as well. So RDO is our community-supported OpenStack distribution. So at openstack.redhat.com, and it gives you everything that you need to try out OpenStack on Red Hat Enterprise Linux. So there's an installer called PackStack that comes with it. There's some quick start instructions that you can have OpenStack up and running on one node within 15 minutes. I think you'll be really surprised with how easy we've made it, so please check that out. And with that, I believe I have plenty of time to take some questions. And also now would be a great time to fill out that sessional evaluation. And if you need a pin, there should be a bunch on the table in the back of the room. OK, question over here.
All those different databases and the different components, are they the same database or are they different?
OK, so the question there was, when I went through all the components, I showed that many of them had a database. And the question was, are those all the same database or are they different? They can be different. It's up to you. There's no reason it has to be the same one.
But as long as their technology is, if they are MySQL, they are all MySQL.
They don't even. So the follow-up question was, do they all have to be the same database technology? If you're using MySQL for Nova, do you also have to use MySQL for something else? And no, you don't. It can be completely different. It's localized to each service. Question here?
Databases are supported.
What databases are supported? From an upstream perspective, it uses a library called SQL Alchemy. So it's anything that the SQL Alchemy library supports. Now, what we test and support the most in reality is it's mainly MySQL. Now, Postgres should work, but MySQL has the most backing in the project and is going to be what you have the best luck with for now. But we've also put a lot of work in to make Postgres work well. So, question here?
The typical hardware footprint for like a primary, like a first-time attempt to install this.
So the question was, what kind of hardware blueprint do you need to do like a first-time deployment? So it really doesn't take much. You'd be surprised. So the resources that take up the most are when you're running virtual machines. But if you're really just trying it out, you really don't need much. I mean, I do development almost entirely in a virtual machine. I run all of OpenStack within a virtual machine, usually with about 2 gigabytes of RAM. And one CPU is fine, and that's fine. I get all the work done I need to. And interestingly, in the upstream in the OpenStack project, every time a patch is submitted, before it can go in, it's tested automatically by a CI system. And the CI system is creating instances in public OpenStack clouds to test it. So in Rackspace and HP's cloud, I believe. So it creates a VM there, and we install all of OpenStack and run lots of unit tests and lots of functional tests just within the VM. And so that works fine. You really don't need much just to try it out. It just depends, do you care about the VM performance or not? If you care about the VM performance, then you probably want to try bare metal. But
Back a follow-up question. How would you then, if your boss makes you put it into production after you've done the test on one node, how do you then break it out?
So the question was, if you've done a proof of concept and then you want to put it into production and break it out into multiple nodes, is that easy? Honestly, I would just start over, probably. But it's not that hard to add nodes. So if you started out on one nice bare metal node and has everything running on it, that works fine. And then what you can do to start scaling from there is add compute nodes. So you would still have the one node that runs everything, and then each additional node, all it runs is the Nova compute service, and it sort of kind of plugs itself in and becomes additional VM capacity. And at a point, when you have enough compute nodes, you're not going to want to run VMs on the main one anymore that has all the different control services. So what you would then have is a controller node that runs everything except the compute service, and then a bunch of compute nodes. So that would be sort of like step 1 and step 2 of starting going. So you can do it. It'd be just a little bit more manual. Just kind of depends on if you're going sort of one machine at a time, or if you're trying to go from 1 to 15 nodes or something, whether I would start over or not. Question here?
So you mentioned ironic at the beginning of your presentation.
Mhm.
I also heard yesterday about Foreman. Is there a difference between the two projects? Are they converging with
So the question was, I mentioned Ironic as sort of a new OpenStack project that's doing bare metal provisioning, and then we also have Foreman. What's the difference? So effectively, you've got two things that are solving. I mean, there's two things solving the same problem, and then it'll be yet to be seen what really takes off. So I mean, yeah, they do overlap.
So they are one and the same?
No, they're not one and the same. They're different, but as far as like conceptually, what we're talking about is the same thing. But some people decided that they wanted to be able to deploy OpenStack with OpenStack, which is actually a little bit mind-bending, but also really, really cool once you get to looking at it, and that's part of that effort. And we're actually getting involved in it. Sorry, go ahead.
Which effort?
The OpenStack on OpenStack effort, or OO. So that's what sort of Ironic is part of. So what this...
Using an OpenStack cluster on the side that'll build and manage other OpenStack clusters.
Exactly. So yeah. So what he was saying is just clarifying that what this is all about is having, so you start with a small OpenStack deployment, which then deploys, does bare metal provisioning for a much larger set of machines that's sort of like your real cloud, and that's deploying OpenStack with OpenStack. So you could spend a whole hour talking about that, but it's something you should, to search up later. It's a very new effort, but there's a lot of people working on it. Question out there?
So one of the slides you mentioned that Python, so the audio is Python-based, or one of the slides say that all?
So I think the question was, I mentioned Python at one point, and are you looking for clarification that everything is Python? Yes. So everything, every service that I talked about here, the actual one's OpenStack, not the database, not the message queue, but all the OpenStack components are all written in Python. Yes. So RDO is sort of our distribution of OpenStack. So all that stuff is also Python. The installer is it's Python, but it also uses Puppet. So PackStack is something that we ship with RDO, and that is a combination of some Python code, but also Puppet modules. And Puppet modules are what actually do all the provisioning, all of your nodes to get it up and running. Question here?
The message protocol as being, let's say, in between the nodes, is it running on each and every node?
I'm sorry, I misheard it.
The message protocol.
Yes.
You drew it as in between, kind of glued together, but is it running physically on each and every node?
Okay, so the question was, I drew a message broker in a lot of the pictures, and I showed it in between services. Is it running independently, or is it running on each node? It is running independently, so it would be kind of like, it's kind of like your database service. You may have a server just for your database, and you probably would have a server maybe just for your message, well, depending on how large your deployment is, but it is something that runs separate, not typically co-located. If your deployment's small enough, you can co-locate it with some stuff, but it's one thing that you run separate. Question here?
That's a single broker, and is it clustered?
So the question is it's a single broker, is it clustered? So the project that we use to do this is Cupid, and Cupid does, it is a single broker, but it does support clustering. And it's well documented in the Cupid documentation. If you want to go look at how that works. So,
You're using it as clustered rather than
yeah, well, it kind of depends on your scale and HA requirements. When you start it out, you may not do that, but the clustering mode is supported. Yep.
What do you mean by object storage in this context, and what goes there?
What do I mean by object storage and what goes there? That's a pretty good question. So here's a use case. Wikimedia uses it, and so I think it was for image thumbnails. So they have a whole lot of images, right, for Wikipedia, and they need a place to put them. And so the object storage API abstracts that problem away. So it's a massive amount of storage, but prevents a very simple API of, I have a thing, I want you to store it somewhere for me, and when I want it back, I want you to give it to me, via HTTP. So, when it has this enormous amount of images to do, it puts them in this object storage, blob of data storage, and then, it has HTTP URLs to get them back. Does that make sense? Okay, cool. So what data you put there is totally up to you, but that's sort of an example use. Yep.
MariaDB?
MariaDB?
Yeah.
It's compatible with MySQL, right?
Yeah.
Then it should work. I mean, I haven't tried it personally, but as far as I know. Question back here.
How do you create images?
I'm sorry, I can't.
How do you create the images?
How do you create the databases?
No, the images.
Images. How do you create images? Okay, so sorry. The question is, how do you create images? So OpenStack itself does not have a project right now for creating images. Now, it's something that that we're looking into and we'd like to build, but there's not one yet. Now, in RDO, our community distribution of OpenStack, we ship a project called Oz, and Oz it's probably for building images for you. So we ship something. It's just not officially part of OpenStack. But Oz, it uses source media, so like the source ISO, for example, and it like creates a local virtual machine and like does an automated install through it, and you end up with a basic disk image. And you can configure it to put stuff in the disk image if you want. So that's typical what we've been using is Oz, but there's not like an OpenStack server. So that would be really cool. And I would, I wouldn't, if when someone's up here talking next year, I wouldn't be surprised if that's another one of the blocks up there as an image building service. Yes.
I think I saw in another presentation somebody was mentioning how Rev can tie into export and import into it. Is that true? Is that a common use practice?
Okay, so the question here was, in another presentation, there was a comment about Rev integration, import and export. And so there's not built-in integration exactly, but what it can do is they use the same format of disk images. So you can have like a QCal2 image from Rev, and you can import that into OpenStack and run it. But it's somewhat of a manual process. There's nothing like built in to either one that I know of that does that. So that's just the current state of things anyway. I wouldn't be surprised if we end up with some, I guess, more native integration at some point. But yes.
So beside the boxes, the components that you have, you mentioned that there is a DB component, a relational database component as well.
Mm-hmm.
So what is the thing that is really specific to DB that is, because you already deal with relational database presentation.
Yeah, so I guess the question was some clarification about what the Relational Database as a Service project will provide that's new and upcoming. And so that's not it's not really intended for the infrastructure itself. It's intended as a user of the cloud. In deploying something to this OpenStack cloud, my application is going to need a database. And to simplify it for me, instead of me having to install it and configure it manually, it's an API call to say, I want a database, and it needs to have this storage capacity and whatever, and it handles all the details of that for you, and then you just have connection details. So it's just taking one thing away that you have to set up manually and giving you an API call to create a database. So it's for the user of the cloud, if that makes sense. Question there, yes?
So you said that to take care of the scalability issues inside the Nova cell, you made Nova cell because you have scalability at distance. In the messaging state, inside the Nova cell, how is the logging going to see within the cell? Why the messaging on that cluster on the Nova?
How is the, did you ask about logging? Okay. So he was asking about when you distribute a large deployment in cells, are you talking about notifications or log files? Notifications. So the stuff that consumes notifications, you would consume it from each cell individually. So you'd connect to each one. That's how it works right now anyway.
So the AMQP services, again.
I guess real quick, so I guess I'll answer your question here in a second. So thank you all. If you guys want to step out, and feel free to come up here and talk to me, I'll answer as many questions as I can. Thank you very much.